Hello, Chem students. Welcome to Chapter 5, the periodic table. What you will find as you go through these slides, you're going to learn a lot more about the periodic table that you did not already know. The first couple of slides will take you through some of the different aspects of how the periodic table came to be and why the elements were arranged the way that they were. So you can actually read through those slides if you would like. What the part that I want to get straight to deals with slide number, this one, okay? So as you take a look here, this talks about the periodic law and how those properties were arranged according to increase in atomic number. It's very important that you go back and look in your notes if you forgot any of this information, because what you're going to also find is that this particular periodic table also appeared in chapter 4. So my recommendations is that you go back through this particular chapter 4 to look over what you see here. Now, as you recall, elements are arranged according to their groups or periods. So if they're in groups, they are also referred to as vertical columns, and there are 18 groups. And those groups are based upon elements with similar chemical properties. Now, when you look at the periods, they go horizontal. They're like horizontal rows straight across. Again, within that row, they have elements that are shown within a range of properties. Now, something else you need to be aware of. There are certain terms that your periodic table will refer to, and in the homework problems. So here you'll see where they say representative elements or main groups. Those are in group A. And if you look on any periodic table, you'll see that there's A and B elements. A, again, are representative elements or main groups, and B's are considered your transition elements, okay? And those are found within the middle part of your periodic table. You also have elements that are called inner transition elements, and they're found at the very bottom, and they're often referred to as your rare elements. Now, speaking of which, I'm going to give you the overview here. As you can see, we have the inner transition elements, and they are divided into lanthanide and actinide series. And the two listed here at the very bottom, okay, you will notice those are your lanthanide and actinide series. And the reason why they took them out of the periodic table is to shorten this. Now, as I continue, there are several families that have common names. And for instance, as we talked about before, on the worksheets that were provided, group 1 are called the alkali metals. Group 2 are referred to as your alkaline earth metals. And we know groups 3 through 12 are considered to be your transition metals. Groups 13, 14, 15, and 16 are named according to the head group of that family. So you have the boron, carbon, nitrogen, and oxygen family. And then you also have group 17, which are your halogens, and group 18 are your noble gases. Something else I needed to kind of go back through, and that is to talk about the one slide that I wanted to mention right before I had to pause for a second, and that is right here. You'll notice that hydrogen on some periodic tables appear above group 1 and group 17. Keep that in mind. Hydrogen is not a metal. Although it behaves like a metal, it is not a metal. It is actually a halogen, okay? So although it appears above the group 1 elements of metals, above group 1 alkaline metals, it is not a metal. It is truly a halogen, and it appears on some periodic tables above group 17. That is part of period 1. Now, there are 18 groups, as I noted before, but there are two different ways in which the periodic table is referred to. There's the IUPAC, and sometimes you will hear that name, but that's in order to differentiate the groups. So you'll see where you'll have both A and B designations with Roman numerals, but if you see that, do not get discouraged by looking at that wondering, what does this mean? They're just used to denote the differences between groups and then the IUPAC symbol. So that's pretty much all that represents. Now, again, as I mentioned, the IUPAC, they proposed a numbering system because those Roman numerals and letters were very confusing for most people. So to keep things consistent, we just refer to them as group numbers. And in my civics class, we talk about that as well. Now, here's something else you need to keep in mind. You need to take out your periodic table and have this particular statement in your ear, okay? So have your periodic table out. I'm going to give you 2 seconds to get it. And I'm going to explain what you should see in terms of the atomic radius. In other words, how big those elements are, okay? Now, if you got your periodic table, let's go. Now, as you look at the atomic radius, it decreases as you go up a group. So for instance, if we look at group 1, as you start from the bottom and work yourself all the way to the very top, the atomic radius will actually decrease. If you go from left to right across a period, the atomic radius also decreases. So now I'm a visual learner, so I'm going to give you all a visual illustration of this. All right, so take a look at this particular chart. Remember, as I said before, as you start from the very bottom, right here, so let's take group 1, for instance, and we're looking at cesium, however you want to pronounce it. As we go up the group, notice how small the radius becomes. If I go over here to, let's say, group 13, start at the very bottom with thallium, go all the way up to boron, the radius gets small. If I start in period, let's say period 2, okay, you will notice here where your elements go from left to right. Notice what happens with lithium. As you go from left to right, it starts off with lithium all the way to fluorine, and notice what happens. It becomes very small. Notice in the middle, transition elements show many exceptions to the general trends. So, we typically don't really talk about the transition metal elements unless we're going to give you specific facts about specific elements within that particular group. Atoms get smaller as you go from the bottom to the top, okay? So just keep that in mind because there are fewer energy levels on the atom. So also keep that in mind. And we're going to get into energy levels later on. Now, in terms of the atomic radius decreasing as you travel from left to right, that's because the number of protons in the nucleus increases. So again, these protons draw energy towards those electrons that are in the nucleus, okay? Now, in terms of the metallic character is basically the degree in which an element can become a metal. So if you look back at your periodic table, most of your elements are considered to be metallic. But the metallic level or intensity decreases from left to right. And as you go to the further right-hand side of the periodic table, those are where your non-metals are located. And this is the similar trend for your atomic radius. So in other words, as you go from left to right, the metallic characteristic trait tends to decrease. That's where you find your non-metals. And because your non-metals are on that side, they typically don't like to bond with other elements unless they are metals anyway. So here's an illustration here. If I were you, I would jot that down. I would draw the picture out on a periodic table. Those of you all that are in my seated class, you will find this chart in class, this periodic table in class that you can draw on. So notice again that the atomic radius decreases from left to right, as well as the metallic characteristic traits. So notice here in yellow, this is where you find your non-metals. The green portion is your staircase. Those are your metalloids. So they have characteristic traits of both metals and non-metals. This section here, which is purple, my favorite color by the way, those are your metals. Now, as you go from the bottom to the top, the metallic characteristic trait increases as well as the atomic radius, okay? Now, let me also say something about this. Notice how you have potassium, sodium, and lithium. Those are also found in your food, that just as a little FYI. And those elements are very reactive. They have to keep some of them in oil because if they get near water, they can actually spark and trigger an explosion. That's just a little side note. Now, since the properties of these elements follow regular patterns, we can predict unknown properties. And again, that's how the periodic table came to be. Notice here how you can predict what the properties should be just based on looking at a chart. So if I wanted you to figure out what the density should be, you should know by looking at it. Like if I blotted out, let's say 0.53 for lithium, okay, right here. If I blotted that part out right there, then you would be able to tell me that as you go from the top to the bottom, the density increases. Also, the radius increases. However, the melting point decreases, okay, from the top to the bottom. Whereas the atomic mass, it increases. So I would actually take a look at this, to kind of get some idea of how you can predict what the trend would be just based on looking at a graph. Members of a group or family have similar chemical properties. So for instance, if you have the alkali metal groups, which are located in group number what? 1, correct. If somebody said 1 to the screen, you are correct. Your alkali metals have oxides of the general formula for the M2O, and that M stands for metal. So as you take a look at the general trend, again, in regards to those elements that are in the same group, they all have that formula M2O. So that means every element within that particular group will have the charge attached from oxygen. That's where that 2 comes from. And then the charge on oxygen is 1 because of the charges that are assessed with lithium, sodium, potassium, rubidium, cesium, and francium. They all have a charge of 1 because they're in group 1. And I'm going to talk about those charges too, so you'll understand exactly what I mean by that. And again, we're going to delve a little deeper within the next couple of chapters after our break when we get back. And I'll go a little bit further about this because I don't want you guys getting confused about where all these numbers and subscripts are coming from. Now, another thing that you need to keep in mind is that when we talk about levels of electrons and sublevels, there's this thing called, electron configuration. So you have all these different energy levels from like 1s all the way to 5s. Okay, actually they go a little bit further out. And what you keep in mind is that the 1 represents the energy level or the period, and so does a 2. So you have 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so forth. Notice how the less than sign is towards the 1s. That's where you have the least amount of electrons. The further out you go, the more electrons you will gain, okay? And again, here are your blocks represented here. And we're not going to really talk about this particular section just yet, okay? We may come back to this particular section at some point in the semester if we have time. And again, I'm going to skip this particular slide and go straight here to valence electrons. So now let me kind of talk about the valence electrons. Valence electrons are basically those electrons that are in the outermost energy level of an atom. So if I go back to my prior slide here, okay, all the elements that are in group 1 have 1 valence electron. All the elements that are in group 2 have 2 valence electrons. We actually skip 3 through 12, and I'm going to go, and because they're transition metals, you'll notice that we skip 3 through 12 a lot because they have variations of rules, okay? But when you get to groups 13 through 18, you drop the 1 off, and the number that you see left over tells you the number of valence electrons within that particular group of elements. So I know that in group 13, those elements have 3 valence electrons. Group 14 has 4 valence electrons, 15 has 5, 16 has 6, 17 has 7, and group 18 has 8. In terms of electron dot formulas, it's also based upon those valence electrons. Again, I'm going to go over this a little bit more in detail when we get into drawing out the chemical bonds. And we're going to have to learn how to write chemical formulas first in order for you to appreciate how electron dot notation takes place. And again, we're going to delve a little deeper about that. But for the most part, what you will notice here is that the pattern that they're going by is right, bottom, left, top. right, bottom, left, top. That really doesn't matter per se. And again, as you draw the pictures out, you'll understand why when we go through this particular part after we get back from our break. So I'll delve a little deeper about electron dot formulas and how to draw the structures together with chemical bonding. Now, ionization energy. This is basically when you have an atom that is the amount of energy that's required to remove an electron in its gaseous state. So think about ion. That means positive or negative charge, okay? So basically, it's the amount of energy required to remove an electron. So basically, saying this means that you increase as you go from the bottom to the top. What else did we say increase from the, we said what decreases from the bottom to the top was your atomic radius. So you see, the trends are tricky. You have to be very careful in memorizing those trends. So whereas the radius goes from bottom to top in terms of them decreasing in size and left to right decreasing in size, well, ionization energy is a little different because it increases from the bottom to the top. So it gets bigger as you go from the bottom to the top. Ionization energy also increases from left to right. So if I were you, I would draw the arrows on my periodic table to show this particular trend. Here it is again. This is a visual to give you that idea of what we're talking about. Again, I'm going to skip this particular part, okay, because we're going to go a little deeper about the ionic charges at a later date. So the things that I'm skipping over, you're not responsible for right now, okay? And so in summary, you're just basically looking at all the different trends of the periodic table, and that's what I wanted you to know from chapter 5. If you have any questions, reach out to me, and you will have some different notes that you can take along with this particular slide. So just be sure to reach out to me if you have any questions or concerns, okay?